Hi, my name is Elodie Bouzbib, and I'm a PhD student at Sorbonne University. I'm about to introduce Cover, a novel robotic interface providing strong kinesthetic feedback in a room-scale VR arena that we developed with my supervisors Gilles Bailly, Sinan Aliyo, and Pascal Frey. A main challenge in VR is the lack of convincing haptic feedback. While VR aims to create more and more natural interactions, it is still difficult to be able to replicate it entirely. For instance, we can ask how to realistically touch a wall. The user would touch it, push it, or even lean on it, but eventually she would redirect herself towards an exit door. But today in VR, it is common to use controllers. They may vibrate when we virtually touch a wall, but they do not constrain the users, as they only focus on the user's hands, and the user might expect force feedback on her entire body. So eventually, the user is more likely to go through the wall. This presentation aims at demonstrating that virtual reality can benefit from large-scale force feedback, and it shows an interface that enables it. One of Cover's main features is large-scale force feedback. It has a sufficient robustness for users to actually lie or push on it. And moreover, it can reach any location of the arena. Here, it actually displaces itself to overlay 3 different doors without knowing where the user is about to interact. Cover is a Cartesian XY robot moving over 2 axes like an XY plotter with pulley belt systems. It is mounted over the ceiling, and it displaces a physical column to overlay physical objects over a large VR arena. So now, how to interact with Cover? When no interaction is required, Cover actually remains out of reach, and users can wander in a whole arena. Cover does not constrain the users to hold continuously a controller, and it actually encounters the user when interaction is required. Now that we're interested in interactions, let's talk about the available interactions whenever Cover is static, which means that it doesn't move unless it is for reaching a position, an object of interest position. The force transmitted in this configuration is then from the user to Cover. On Cover's panels, we can create some haptic rendering to overlay objects or even suggest shapes or codes to the users. For instance, here, the user is exploring a code with her bare hands because her vision is blurred. We also can attach props to Cover's panels for users to perform mechanical manipulation or directed manipulation to actuate the props as per the slot machine. Cover can also transport objects for the users to manipulate. Here, she freely manipulates a cube to fit it in the locker, but the cube is actually too big to fit in the locker, and she will feel it because Cover enables both free manipulation of untethered objects and interactions between objects. Whenever Cover is static, it allows both bare hands exploration and manipulation with over 100 Newton perceived stiffness. But it also allows multiple postures while remaining static. We've seen that Cover enables the users to push hard on it, but other postures are available, such as sitting comfortably on a chair or going into Cover to reach a higher target, or even going underneath Cover whenever playing an obstacle course game. And with its robustness, Cover also allows for the users to lean on it. Users can also receive interactions from Cover whenever it is dynamic. In this configuration, Cover transmits the force to the user. Cover's key feature is to enable whole body interactions with large kinesthetic feedback, and these are actually even stronger whenever we take advantage of Cover's displacements. For instance, users can be led through forces and pulled by Cover as if they were traveling with a magic broom. They also can be literally transported by Cover within the arena, as cover can actually carry over 80 kg of load capacity. Cover can also initiate the interactions and simulate, for instance, the crossing of a ghost through the user's head. Whenever cover is dynamic, it provides large-scale force feedback and novel interactions, such as transport by sitting on cover or transport by being pulled through traction forces. But for all interaction to happen, the main concern is to physically and accurately match the virtual object of interest positions prior to the user. So how to ensure that cover is at the right position at the right time? How to decide what to overlay? Let's take a top view of our arena. The implementation is done on Unity, and here we can see the avatar at the center of the arena. If we add an object of interest, it will be straightforward for the user to actually reach it. But now let's add cover at the bottom right of the arena and ask ourselves, what trajectory should cover follow? So the shortest trajectory from cover's origin to an object of interest would actually collide with the user. So we then decided to add a cone-shaped virtual obstacle to the user on Unity for cover to avoid it pretty smoothly. A way to do it is to attach a proxy to cover, being a ball subject to gravity on Unity. So this proxy ball will hence respect the physics of the engine and lead cover around the cone-shaped obstacle. Now we need to give a common position to cover. So let's imagine a non-deterministic scenario where the users are free to interact with any object of interest. Non-deterministic scenarios introduce uncertainty regarding the object that cover is about to overlay. In order to be available prior to the interaction, we hence need to give a common position to cover. Naturally, cover will first move towards the objects of interest barycenter, their centroid, to be equally available to overlay all of these objects. So we can see here that cover placed itself at the barycenter of all the objects of interest. The idea is for cover to move accordingly with the user's displacements and more precisely her intentions. Whenever the user is moving, her intentions are changing. So to predict which object of interest is about to be interacted with, we calculated a weight per object of interest as a function of the user's orientation and distance to them. Cover will hence go at the weighted average of the object of interest position, and when a weight is equal to 1, the object actually has been chosen. So we can see here that the proxy leading cover is moving towards the object that has been chosen by the intention algorithm. The weight depends on the distance of the user from the object as well as its orientation. The relative contribution of the distance and the orientation depends on an omega factor. It is not clear what the optimal value for omega is. Should the distance or orientation be more important to predict the next object of interest? We thus conducted a technical evaluation to estimate the optimal value of omega. The optimal omega will allow to predict correctly which object is about to be interacted with. We also wanted to evaluate cover's accuracy depending on the number of virtual objects of interest within the scene, and we wanted to validate that cover physically follows its proxy and hence that cover is safe around the user. So we performed a data collection of 6 users that were asked to perform an explorative task and touch target balls at random positions and orientations among distractors. So we controlled the number of distractors from 0 to 4, and they appeared in a pseudo-random order. Participants performed 10 blocks of 5 conditions. So we recorded a total of 300 trials, some trials having a single target object with no distractors, and some trials having multiple distractors. We recorded the user's location and orientation and the objects of interest positions. Then we had a simulation phase where we used users' data to physically run cover in the arena. In the data collection, we had real users but no column. And in the simulation, we used users' data, but we used the real column. So we perform a simulation in an omega fitting phase where we change omega and measure the success rate of cover reaching a virtual object of interest prior to the user. We also measured the distance between cover and the target when a collision occurred. We first performed a broad exploration of omega, then we refined it to find the optimal one for each condition. Here, for instance, we can see that the user is moving and the weights are changing accordingly with it, and the proxy and hence cover are moving according to those weights. The average accuracy between the carriage and the target centers was 1.8 centimeter over 300 trials. We also measured the distance between the proxy and the carriage centers. The average was below 1 centimeter, which ensured that they actually shared the same trajectory. We also found that with omega at 0.175, we had a little over 80% success rate. The orientation to an object of interest is hence way more prominent than the distance to it. But let's think of a way to increase the success rate. So we can picture a basketball game. Players will most certainly interact with the ball prior to interacting with the hoop, right? So we can hence assume that the ball is more likely to be interacted with. So if we translate it to cover, cover providing a ball first would hence make more sense than cover being at the hoop position, right? We can then add prior probabilities on what we call a scenario-based model, which is still non-deterministic as it doesn't force a position on cover and still depends on the user's intentions. We launched a second simulation by adding 75% prior probabilities on the target to be interacted with, and this improved the prediction with an average success rate higher than 95% over the 300 trials. Now that we defined that cover allows non-deterministic scenarios and whole body interactions, we conducted a user experience to validate the implementation and verify that cover does not collide with the users in real-life experiments. We also wanted to evaluate the strength of our force-related interactions on users. Another goal of this experiment is to evaluate if large force feedback is appreciated in VR and what were the users' favorite interactions with cover. So users were asked to climb on a stair, and as we've seen previously, they also had to push as hard as they could on magic walls. They were then transported on a magic broom and pulled through forces, crossed by a ghost, and physically transported in the arena. No collisions with the users or mismatches regarding their intentions was noticed during the games, so this validates our safety and software implementation. Also, users spontaneously pushed hard on the walls and ranked their own forces with a 5.5 grade on a 7-point Likert scale. The force received by cover while being transported was ranked with a 6.1 grade on a 7-point Likert scale. So this validates our mechanical implementation concerning cover's robustness. In terms of interaction, the global enjoyment was above 6 over a 7-point Likert scale, and the favorite interactions were being pulled through forces with 37% of the votes, while the favorite one was the transport with 63% of the votes. So we can hence affirm that VR can benefit from large-scale force feedback and that there is a promising future for whole body interactions with large force feedback. To sum it up, we presented cover, an interface allowing whole body interactions and strong kinesthetic feedback in a room-scale arena. We presented the elaboration and evaluation of a user intention-based model allowing non-deterministic scenarios, and empirical results on the user's most enjoyable interactions using cover. Thank you for watching this presentation.